record because I get yelled at if I don't. All right, here we go. So today we're going to start talking about the mean value theorem. See, yeah, exactly. I would get recorded. I would get yelled at. We're going to start talking about the mean value theorem. Now, is the mean value theorem, has anyone seen it before? Because for me, it's such like a quintessentially obvious thing that I forget that some people probably, or maybe in fact, most people haven't seen it before. So has anyone seen the mean value theorem before? Is it like a totally new thing? Nobody's seen it? It's like this mysterious thing. Yeah. Okay. So this is actually, so the mean value theorem, it's this funny thing because it's actually a real point of contention at like teaching conferences, believe it or not. So when I go to teaching conferences, I tell people that teaching the mean value theorem is stupid. And people are like, no, how can you say that? The mean value theorem is great. And I said, yes, of course the mean value theorem is great. It's one of my favorite theorems in first year calc, but you shouldn't teach it unless you're teaching like an analysis class or a proofs class. So the thing is, they teach this in like 135, 136, 132, 134 and stuff like that. And I said, that's stupid. You shouldn't do it there. So this holds a special place in my heart because it's also gotten me into a lot of trouble at teaching conferences. Okay, so anyway, it's such a fun theorem though. So we're going to have to build up a little bit in order to be able to get to it. So we have to talk about a couple of things, build up some lemmas, and before I can even state it and tell you kind of what it is that I'm trying to do. Some of these words though are probably not going to be new to you. You're like, yes, I know what a max is, right? I know what a critical point is. Those are probably not new. But let's define them anyway, just make sure everyone's kind of on the same page. So if f is a function, let's just say from D to R, something like that. From D to R, a point C in D is a local max. Okay, and in brackets here, I'm just going to put min because I don't want to write out an entirely separate definition for minimum. So I'm just going to put the appropriate changes in brackets. If there exists some row greater than 0 such that f of x, which one did I do? Max is less than or equal to f of c for all x in D intersects c minus 0. Oh, shoot, I forgot to put my brackets in. F of x is greater than or equal to f of c. Right? And I mean, this is kind of cheating because we've already used the notion of maximum and minimum when we talked about the extreme value theorem. But I mean, this is kind of more like local max, right? When we were talking about the extreme value theorem, we were talking about the like the real maximum of the function, the global maximum. This is a definition of a local max or min, and it says that you're the maximum nearby, right? You don't have to be the maximum. You don't have to be bigger than f of x for all x in the domain, just nearby, right? And so that's what this D intersects c minus rho, c plus rho is. It just guarantees that there is a little interval around which you are actually the maximum. Okay, so that's what a local max and min are. And again, for a minimum, all you're going to do is switch the inequality, right? So the inequality becomes f of x is greater than or equal to f of c. And then, you know, while we're here, we might as well say you're a global max or min if you're the biggest thing, you know, in the entire domain, right? We say that C is a global max or min if f of x is less than or equal to f of c for all x in the domain, right? Oh, and then stupid brackets. Again, I forgot again. For all x in D, right? So again, you just have to be big, bigger than everything nearby you, right? And what do I mean by that? So if we draw a little picture, here's the x-axis, and I do something like, right? So the global max is this big thing right here, right? This is the global max. But this thing has lots of local maxes as well, right? These things all here, these are local maxes. Local max. Excuse me, why is am I getting sick? I hope not. Okay, and then we have local min right here. Okay, so these are the local min. And I haven't drawn this in such a way that like there's an obvious global min. Well, let's say that these are both global. Well, no, because there's kind of global mins over here. So let's say this is a global min. And then the rest are local mins. And now I'm going to be lazy and just write it like this. Right, and local min like that. Okay. Global likes the row goes to infinity. Yeah, exactly. Yeah, that's a great way of thinking about it. Yeah, it's like the row goes to infinity. Okay, so that's the idea. Now, I imagine you've seen these sorts of definitions before, and the way that you would handle this in a traditional sort of like calculus-y class is that now we'd spend like 2 or 3 weeks talking about maxes and mins and the first derivative test, second derivative test, blah, 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 right? That's not really our interest. We don't care because that's an application, and we don't do applications in this class, right? We don't study things because we care about how they're applied. We study things because we just think they're interesting. Okay, so without kind of diving into that too much, we're going to just pivot straight into a new definition. So definition, if f is a function, so again, so if f, so this time, again, I'm going to be a little bit lazy and I'm just going to skip what the domain and codomain are, but, you know, so if f is differentiable, we say so we're going to define a critical point here. So those of you who already know what a critical point is, you can just write it down. So we say that a function or a point C is a critical point if the derivative at that point is 0, right? So if f prime of C is 0. So if f is differentiable, that a point C is a critical point of f if f prime of C is equal to 0. Okay. And again, if you were kind of like doing a standard first year calc thing like 135, 136, you would probably also say that the derivative does not exist. That's usually how critical point is defined in those classes, precisely because, again, they're interested in determining maxes and mins from an applied viewpoint. And it's possible for a max or min to also occur in a place where the derivative doesn't exist. So they kind of throw that in there. But as you go and you do higher mathematics, you're kind of not interested in places where the derivative doesn't exist. So for our purposes, we're basically just going to say that a critical point is anywhere where the derivative is equal to 0. And I hope this doesn't come back to bite me in the butt later, but we'll see, right? Live and learn. So I'm going to say just for now, it's only where the derivative is equal to 0. And like I said, outside of first year calc, nobody calls a critical point. Like this is the definition of a critical point always. It's just there is this kind of trend in first year calc to also be like, oh, where the derivative doesn't exist, that sort of thing. And here, let's just do a quick little example. So let's say find the critical points of this function. And again, I'm not going to give it a domain because whatever. Okay, so let's take this function. And of course, if I did impose a domain and then you found a critical point that was outside of the domain, you would throw it away, right? But generally, the way that you do this thing is you kind of don't worry about the domain, you differentiate, you set it equal to 0, you find out where its possible critical points are, and then you take the critical points that are in the domain of the function, right? So in that sense, I'm saying like we don't care about the domain here, just because the process is going to require us to find them all anyway. All right, so what are we going to do? Let's differentiate this function. And again, you don't have to wait for me. I think you all know how to do this. So differentiating. Okay, I'm going to use the quotient rule. All right, somebody double check me. So derivative of the top times the bottom minus the derivative of the top, or the bottom times the top, all divided by the bottom squared. So that gives me 1 minus 3x squared divided by 1 minus x squared squared. And we want to set this thing equal to 0. So this is obviously 0, just where the numerator is 0, right? So this will tell us that 1 minus 3x squared has to be equal to 0, which is what? X is equal to plus or minus 1 over root 3, right? And we're done. Is it 2x squared? It is, but then I multiplied it by the top, right? So that's why I got the x squared. You're right. I kind of I cheated here, but let's double check. So it's going to be, oh, you're right. It's going to be plus. Is that what you're saying? Yes, it's plus 2x squared. Okay. And that's going to give, and then I wrote it as minus again anyway. So this will give me plus x squared. Oh no, now it has no critical points. Damn. Well, this example didn't work out very well. So there are no critical points. Can I fix it if I just change the denominator to plus? Okay, so now what's going to happen? So I'm going to get derivative of the top times the bottom. Sorry, just wait. Don't write anything. Don't write anything down. Let me see if this fixes it. Minus, right? I think this fixes it. Does that seem right? Derivative of the top times bottom minus the derivative of the bottom times the top, all divided by the bottom squared. Okay, I think that fixes it, right? So now I actually do get critical points again. Right? Does that look right? Did I screw up? I think this is just like the perfect example of this class is the moment I had to do a computation, went out the window, right? There was no chance of doing it correctly. Everyone agrees then? This is the correct derivative? That looks okay. Is anyone, any objections? As turning point, maybe. I'm not familiar with that notation. What's the definition of a turning point? Yes. Yeah. Right. In the sense that so again, if you think about, there's no y here, but if we said if y is equal to f of x, then the derivative of y with respect to x would be the derivative of f. And exactly where you say dy dx is equal to 0 or infinity. And in your case, that infinity includes what I was kind of saying in the previous definition, where a lot of people include the does not exist portion, right? Where they say the function is not differentiable. So yes, in this case, it is the same definition, at least as what we would kind of typically see in a first year calc class. For our purposes, I'm going to throw away the or infinity portion, but otherwise, if you throw that away, it is the same definition. Yeah. No problem. Okay, everyone's good? I can tell everyone's eager for a theorem / proof. So let's do that. And so you say okay, well, why talk about critical points? And for those of you who've gone, I've seen this sort of thing before, you know what's coming, though you probably didn't prove it. So proposition, if f, I am going to give it we're doing a theorem now, we should be precise. So if f maps a, b to r, do I want it to be differentiable on the whole interval? I probably don't need it to be differentiable on the whole interval. interval. So is differentiable at a point C in AB, and C is a local max or min of F, then F prime of C is equal to 0. That is, C is a critical point. Okay, so this is a really great theorem. It says, or proposition, it says if you have a local extremum, so you're either a local min or a max, and you're differentiable there, then in fact your derivative had to be 0, right? That's what this theorem is saying. If a max or min occurs at a place where you are differentiable, then you can say, yes, in fact, that the derivative has to be 0, okay? Now, if you're taking notes and you're copying this down, I'm going to scroll up here in a second, but I will come back to this. But what I want to do is I just want to go to my little picture here. And yeah, one thing that we notice is that every single one of these sort of maxes and mins, if we were to like draw the tangent line, it does indeed seem to be, okay, this one's not drawn super well, but it does seem to be horizontal. Now my global max here, or my global min over on the left-hand side, I would say is actually not differentiable there, right? Because remember, in order to be differentiable, you have to be defined in an open interval, so you have to be defined on either side. So the fact that this global min kind of occurred at an endpoint does mean that, you know, it's not differentiable there, and so therefore it doesn't have to satisfy this theorem. But if we look at the interior, right, and that's what this theorem is saying, if you look at the interior, every single one of these local maxes, mins, and therefore global maxes and mins has a horizontal tangent line, right? So that's what we want to prove. We want to prove that that's not a coincidence. That actually always happens. And the proof's not terrible. It's a little bit technical just because you have to be like, and carefully like set stuff up. Let me just be careful about how I want to do this. Right, okay. So I'm going to do the proof for local max. The proof for local min, you would just use the negative of the function. Okay, so I'm going to say without loss of generality, suppose C is a local max. Okay, and if it's not a local max, apply this theorem to negative F. If not, apply this result to negative F. Okay, because all we're trying to do is we're trying to show the derivative is equal to 0. So if I show that the derivative of negative F is equal to 0, well, that tells you that F was equal to 0 as well, right? The derivative of F was equal to 0. So, and what the benefit of the negative does is it's going to switch maxes into mins and vice versa, right? So if you have a local min, you take negative F, it now becomes a local max. You show that the derivative of the function there is equal to 0. That means negative F prime of C was equal to 0. That tells you F prime of C was 0. Can I repeat which part? The part that I just repeated? Maybe that was just by accident, or just let me know which part that you want me to repeat and I'll do it again. Okay, right, and just again, just think about it. So hopefully everyone's fine that if you take the negative, maxes turn into mins, and then again, if you show, I'm going to erase this bit, but if you show that negative F prime of C is equal to 0, well, that told you that F prime of C was equal to 0, right? So that's the idea. So we're going to prove it for maxes, and then for mins, you just say do it to the negative of the function, and you're done, right? You don't have to like repeat the whole proof or anything like that. So we're going to suppose C is a local max. Let's say rho greater than 0 be such that f of x is less than or equal to f of c for all x in AB intersect C minus rho, C plus rho. Right, that's just a little bit of a technical bit, because again, we are only guaranteed we're a local minimax. Are we using limits to create an interval? No. So I have this interval here, and this interval is only exists because, again, if I look, if I go up to my picture, and let's say I look at, which one do I want to do? Let's say I look at this local max right here, right? This one. So I have to guarantee that it's only true in some row, right? There's only some interval on which it's the biggest. Like maybe I take something like it's bigger than everything nearby. Maybe I would take this as being my row, because if I let my row go too big, then it's gonna start to include this stuff, this part of the function, which is actually bigger than this, right? So all the row is doing is saying to look near enough, close enough nearby so that your function actually looks like it's bigger than everything else, right? There's a bunch of like little mountain peaks, and what you're going to say is rho is just making sure that I am the tallest mountain nearby. There might be a taller mountain if I go further enough away, but I am the tallest mountain nearby, right? Intersection just guarantees, because rho is a symmetric interval, but you could actually be like, let's say that you're on the interval like 0, 1, or let's say open 0, 1, right? And you are the biggest thing, you're standing at C is equal to 0.1, and you find a row which works, and that row is equal to, a half. So now you're going to necessarily be too big. And what you could certainly say, like, I'm going to guarantee and choose rho to be small enough that I stay entirely inside of my interval. You could do that, right? Because once you have a row that works, you could certainly use any smaller row as well, because you're just interested in being bigger than everything else nearby. But so, yeah, I mean, absolutely, you could say that and it would be fine. It's really not going to come up again in the proof. So it doesn't matter whether you want to say that or just take the intersection, but both of them are fine, right? So it just keeps us from kind of leaving the interval. Yeah, so P is like an exactly Sultan, yeah. So P is like the restriction to the domain we are considering. Yeah, exactly. Or it's, that there's an interval that works, and then you've intersected it with your domain just to guarantee that you stay in your domain, right? That's all we're doing, is just guaranteeing that you stay in your domain. Isn't this what we did in assignment 5? Depends. I mean, kind of. We're not going to use that fact directly, but we did do something similar. Yeah. In that case, rho was equal to delta, and we don't necessarily have a delta hanging around here, but we did do something similar. In part just because anytime I want to make an open interval, I often use rho. So you get, I think you've all seen this a couple of times now, but I usually use rho and I use it separately than delta, just to say, oh, look, there's some open interval that exists. Maybe it's related to delta, maybe it's not, right? That sort of thing. So I wouldn't worry too much about this. This is just a technical little point to say, let's make sure that we stay inside of our domain, right? That's all that's saying. We're just going to stay in our domain. But again, you absolutely could say, just choose rho small enough to make sure that C minus rho, C plus rho is entirely within the interval AB. You could totally do that and it would be okay. Okay, so what do we know? So we know that 0 is less than f prime of C, right? Because I've assumed, oh no, wait, no, that's not what I'm trying to prove. What do I know? So we know that f of x is less than or equal to f of C, right? For all x in here. So that implies that f of x minus f of C is less than or equal to 0, right? So I just put the f of C onto the other side. And again, implicitly, this is for all x in, AB intersects C minus rho, C plus rho. And then I'm going to divide by x minus C, right? I'm trying to get the derivative to show up here. Oh no, actually now I need to break it into cases. So now case 1. So let's suppose that we are to the right of C, right? So suppose x is in AB intersect C plus rho. Okay. And in this case, again, if you were just saying, suppose that you make sure that your c minus rho, c plus rho is in AB, you would just say, suppose x is bigger than c, right? But it's still in your interval. So this is what I'm saying. I'm just saying that x is a little bit to the right of c, right? Because what I want to do is kind of take a look at the limit as x approaches c from the right. So then now I'll get that f of x minus f of c divided by x minus c is less than or equal to 0 for x in AB intersect c, c plus rho. Okay, and does everyone agree? Because here x minus c is greater than 0. Right? So I had the numerator was already less than or equal to 0, and then I divided it by a positive number. So the inequality stays the same. Everyone agrees? All right, hopefully there's nothing too crazy there. And so what this means now is that as I take the limit as x approaches c, well, I'm taking it as from the right, right? Because if you look at my interval here, I've made sure that x is to the right of c, right? So when I limit x towards c, it's approaching from the right. And I get this thing here, x minus c. Now that has to be equal to f prime of c, because we assume that f prime existed in the first place. So it's one-sided limits both exist and are equal. And this limit also has to be less than or equal to 0, right? Because if f of x minus f of c divided by x minus c, if that thing's always less than or equal to 0, it can't magically somehow, when I take its limit, become greater than 0, right? That's not possible. So when I take the limit of this thing, it's equal to f prime of c, and it's equal to f prime of c because we know that that limit exists in the first place. So it's equal to f prime of c, and therefore f prime of c also has to be less than or equal to 0. Okay, does that make sense? Are there any questions about that? Because then what we're about to do is we're about to show that f prime of c also has to be bigger than or equal to 0. And that both of those conditions simultaneously will force it to be equal to 0, right? We're saying it has to be less than or equal to 0. It also has to be greater than or equal to 0. And the combination of those two things force it to be equal to 0. Okay. Okay, if there's a question, throw it in the chat. Case 2 is the same thing, only you take the limit from the left, right? So if now x is in AB intersects c minus rho c, and again, you would say just less than c if you weren't doing the intersection. Now, when I do this division, it is going to actually flip the sign, right? Since x minus c is less than 0, right? Because x is to the left of c. And therefore, when I take my limit, thus the limit as x approaches c from the left, f of x minus f of c divided by x minus c, that's also equal to f prime of c, and this now has to be greater than or equal to 0, right? And so the combination of both of these things is we get 0 is less than or equal to f prime of c is less than or equal to 0, and that forces f prime of c to be equal to 0. Right, and so we're done. So how does this case 1 and 2 change? No, so what you would do, I mean, yeah, so if you wanted to redo the proof, this is an interesting question. So if you wanted to redo the proof now for a, what did we do here? We did a max. If you wanted to change it for a min, what's going to happen here is that this inequality here is going to flip, which means this inequality is going to flip, which means this inequality is going to flip. And it just flips everywhere, right? This inequality flips, this inequality flips. So if you were to do it for a minimum, instead, just every inequality everywhere switches, right? But you would still get it's equal to 0 because you're still going to end up proving both that it's simultaneously less than or equal to 0 and greater than or equal to 0, right? So if you were to do that, like redo the proof, that's what it would look like. But what I'm saying now is we've proven that if you are a max, if you're a local max, then f prime of u is equal to 0, right? So now what I would say is the next case is, suppose that you're a local min. Well, I would say, okay, define a new function, which is negative f. If you're a local min of f, then you're a local max of negative f, right? So that means that by the theorem that we just proved, negative f prime of c, here, maybe let me write it out. So here's how we do the negative thing. So if c is a local min, define g of x equals negative f of x, so that c is a local max of g. Okay, now I haven't proven that. You should do that, right? Just convince yourself that if you take the negative, it switches maxes and mins, but it literally is just write down the definition of, a minimum and then take the negative of both sides. That will flip the inequality, right? By what we proved. G prime of c is equal to 0, but g prime of c is negative f prime of c. And so once again, we get f prime of c is equal to 0. Does that make sense? So the idea is that you don't repeat the proof. You don't have to. Once you know the proof is true for maxes, if you're given a local min, you basically create a new function which gives you that as a local max. Apply the theorem to that new function, and then from that new function, the result that you want falls out, right? And yeah, Salman, so exactly, if you only have continuous, this is an interesting question, right? So if you replace differentiability, the answer is generally no, just because you don't know that the function is differentiable, right? So the theorem kind of just breaks down because you don't know that f prime of c exists, right? And yeah, and this is basically what Stephen is saying, is that you don't know, basically the problem comes right here, right? You don't know that this is equal to f prime of c. So that ends up being an issue. But this is a reason why a lot of people include these, in the definition of a critical point where the derivative doesn't exist. Because either your function is differentiable and this proof holds, or your function is not differentiable, in which case the derivative doesn't exist. And you would still be able to say that, a max or a min corresponds to a critical point. So that's why some people throw that in there so that they can, just say that the word critical point always corresponds to a max or min without having to worry about the differentiability of the function. What would happen if we just take limit instead of one-side limits? I mean, if you just took the limit, there isn't much you could say. It kind of like, if you think about what we've proven here, here, let me draw a function and let's draw a local max, right? Local maxes always kind of look like this. This is what we're trying to actually say. So here's our point here. And this is C. So the case one said, well, let's look a little bit to the right. Here's maybe like, actually here, let me write in C plus rho here. And then here's, C minus rho. And so it says, listen, if you give me any point and I take the secant line, right? So this is going to be, so this point here is my x. Right? So the way the whole proof works is to say, look at the slope of the secant line when you are slightly to the right of a maximum. When you're to the right of a maximum, the slope is always negative, right? And that's what we're saying here. So geometrically, the proof is saying the slope of the secant is negative here. Or let's say non-positive, right? It's always less than or equal to 0. And so that guarantees that as you limit x towards c from the right, you're guaranteed that the derivative slope is also less than or equal to 0. And then when you do the same proof on the other side, you make the same sort of argument over here. Let's maybe call this a different x. Let's call this x prime. And you take the slope of this secant, right? You get f of x prime minus f of c divided by x minus c. And that's always going to be greater than or equal to 0, right? So here we've got the slope of the secant is greater than or equal to 0. And so by looking at these two one-sided limits, this is why we were able to prove that it had to be equal to 0, because it has to be greater than or equal to 0 from the one-sided limit, which is red on the left, and it has to be less than or equal to 0 in the one-sided limit, which is the green stuff on the right. And the only way both of those things can be true simultaneously is that at the actual point, the slope of the tangent is equal to 0. Right? Does that make sense? So this is how the proof works. You say, listen, it's a max. Slopes are negative to the right. Slopes are positive to the left. The only way these two things can reconcile at the maximum itself is if the slope of the slope at the maximum is equal to 0. Right? And you can see if you do the minimum, you just flip the signs. Right? If you were to do the minimum, the slope to the left is negative and the slope to the right is positive. And so it still gives you 0, right? It doesn't care. You wouldn't, like I said, you wouldn't redo the whole proof. You would take the negative of your function and then just argue that its derivative was equal to 0 at your local max point. And that would give it to you. But this is the geometric intuition behind why the proof works. So does that make sense? Does that like help clear up like what the proof is doing? Cool. All right, so that's the idea. Now, okay, let's think about what the theorem actually said, right? So what does the theorem actually say? So it says, if you're a local max or min, then you must be a critical point, right? If you're differentiable. So if you're a local max or min, you're a critical point. So this is great because what you would do normally is if you were looking for maxes or mins, what you would try and do is you'd find all the critical points of your function, and then you would just test them. Hey, are these maxes or mins? The problem here is that this is not an if and only if. This would be phenomenal if this were an if and only if, right? You're a local max or min if and only if you're a critical point. Unfortunately, that's not true. This is a necessary condition, but it is not sufficient. Okay, so note. Being a critical point is necessary for local extrema, but not sufficient. Right? And what I mean by that is that there are critical points that are not local maxima or minima, right? So there are critical points which are not local extrema. Okay, can anyone think of an example? Don't think too hard. For example, can anyone think of a function that has a critical point? Perfect, thank you. F of x equals x cubed has a critical point at, let's say, c equals 0, right? Because its derivative is 3x squared. So certainly, you know, the zeros of 3x squared are just 0. But we know that 0 is not a maximum of x cubed. Right? What about constant functions? In the case of a constant function, you would argue that, so certainly their derivatives are constantly 0, but every point is also both a maxima and a minima. So you're right, that's an interesting example. It's a little bit pathological. Every point on a constant function is both a max and a min. Okay, so Yonje, it's possible that it depends on the domain of the function, right? Because if I said something like, you know, let's just kind of do this on the side. If I define f as the map from 0, well, let's take -1 maybe. R, x maps to x cubed. This function does actually have local max and min, right? If we plot this thing, what does it look like? It looks like, right, like this. And so there are local maxes and mins precisely at -1 and +1. Yes, but you're right. In R to R, there are no maxes or mins. That's absolutely true. But we can see, of course, if we impose a closed and bounded domain, then the extreme value theorem tells us that the max and min must exist, right? It's just the problem is going to be that these are not, right, by the theorem above, you basically need that the max or min occurs on the interior of your set. We would say that this function is actually not differentiable at -1 and 1, right? So the theorem, the proposition above wouldn't apply. The theorem only applies when you look at points that are actually strictly inside of your interval, not potentially the endpoints. So the endpoints you kind of have to treat differently. Can't you also have local extrema without a critical point? So Salman, the only way that that can happen is if your function is either not differentiable, right? That can certainly happen. So for example, the absolute value function, right? So this function definitely has a local min at 0, for example, right? But it's not differentiable there. So it doesn't fall under our definition of a critical point. So it is absolutely possible for that to happen. The other thing that could happen is the x mapping to x cubed example right above it, which is you have local maxes and mins, in this case, actually global maxes and mins at the endpoints, -1, 1. Again, this doesn't contradict the previous thing because first of all, the function is not differentiable at its endpoints, right? Because in order to be differentiable, you actually need to be able to take a limit from both sides. So you can't be differentiable at endpoints. And the theorem actually explicitly requires that we look at an open interval, right? So it is possible. You can definitely have local extrema that are not critical points under our definition of a critical point, but it doesn't necessarily contradict that proposition because the proposition says you have to be differentiable at your point, which means you're defined on both sides. Does that make sense? Everyone's okay? Why is it not differentiable at 0? Because if you take the one-sided, so you should try this one if you haven't done it. If you take the one-sided limits as you approach 0, you'll get +1 in one direction and -1 in the other, right? Like look at the slope of this function from the right. It wants to be the line y equals x, right? Which just has slope 1. And then as you approach from the other side, it wants to be the line y equals -x, which has slope -1. So at 0, it's almost the same sort of proof that we just did where, we said the derivative had to be greater than or equal to 0 and less than or equal to 0 from different sides. And so the only way I could reconcile was to be equal to 0. Here, the slope wants to be +1 from one side and -1 from the other. But unlike 0, there's no way to reconcile these two things, right? You can't be both +1 and -1 at the same time. And so it fails to be differentiable for that reason. It doesn't know what derivative it wants to be. It wants to be both of them. Okay, everyone's good? Okay, so like I said, in a normal calculus class, what you would do is now we would, well, actually now is where we get into the contentious part of whether you would state and prove the mean value theorem. But most calc classes at this point would start talking long and hard about, how to actually find maxes and mins and classify them and do all these sorts of things. Like I said, we're not going to worry about that. But if you want to, you can do some sort of reading. You can pick up any traditional calculus book if you really want to get into that. For the most part, it's just computationally laborious and is not terribly interesting. And truth be told, in any real life, and I've done a fair amount of applied mathematics in my lifetime, the fact that calculus comes up in finding maxes and mins is undeniable. It absolutely does. But you don't usually need to know more than what I've already taught you. So the other calculus classes will kind of go into it a little bit more deeper, talk about a first derivative test and a second derivative test. You might want to look those things up. Maybe I'll make them test questions, or assignment questions. But you don't need to go into the level of depth that like 135 and 136 do. It's just not useful. It's just not interesting. Okay, but if you want to, you can totally do some reading up on that if you want to. I'm pretty much going to pivot now straight into Rolle's theorem. And so if you haven't heard of the mean value theorem, I really figure that nobody's heard of this theorem. Right? Okay, so Rolle's theorem is the following statement. And now we have to be careful about the hypotheses of this statement, okay? Pay close attention to the hypotheses. So if F maps a closed interval AB into R is continuous on the entire closed interval, and differentiable on the open interval, and f of A equals f of B, then there exists a point C in AB such that f prime of C is 0. Okay. Now I claim this theorem is intuitively obvious. Now I want you to try and think about this for a second. Okay, think about what this theorem is stating. Oh, okay, so Adam, yeah, that's exactly how we're going to prove it. Yeah, 100%, you're absolutely right. Is that basically the proof goes, oh, it's continuous, so that it must have an extremum. The extremum, we're differentiable at the extremum, therefore f prime c is equal to 0. And that's exactly the proof. So that good insight there. That's very, very good. I claim though that like even before you started taking this class, if you were taking kind of like a silly analysis or a silly calculus class, right, or a much less rigorous calculus class, this is still an intuitively correct theorem. Even though the proof is not intuitive for them, it's intuitive for you maybe, but it's not intuitive for them. The result is intuitive, right? And does everyone see why, right? Like here's how I would motivate this if I had to teach this in 135, which I would be upset about and would protest about, but would do it all the same. So let's suppose f of A and B are 0, okay? And in fact, you're going to see in the proof, we're going to assume without loss of generality that that is true. Okay, so here's the point A and here's the point B, and they're equal, right? They have the same y value. And now my challenge to you is to do the following. Draw a graph, draw any function that you want that goes through both A and B, is differentiable. Okay, so it has to be smooth, can't have any like kinks or jumps or anything like that. And somehow does not have its derivative equal to 0. Well, of course you can't do it, right? And the essence of this is that, well, if I enter into A, in order to get back to B, I have to turn around, which is kind of this interesting, maybe like it's a turning point sort of idea, right? Maybe that's where that that notation comes about. Like, who was it again? Who said turning point? Right, really. So maybe this is what we mean by turning point, right? Like, if the way I've drawn this picture, if I go up through A, in order to come back through B, I have to turn around. And the exact point where I'm going to turn around is going to be a critical point, right? Right? So I'm traveling up, and at some point I have to turn around to get back to where I started. And it's the same sort of thing. Like in real life, if I told you, go stand at your home, go somewhere else and come back, at some point in your journey, you had to have like turned around, right? And let's say, like I said, you could only walk in a straight line. So you start at your home, I say walk in a straight line, and then eventually, end up back at your home. I guess you could have walked all the way around the earth, but let's assume you can't do that. So what would you do? At some point, you would have to stop and then turn around and walk back home. right? And remember, F prime there is your speed. So it doesn't matter how quickly you're walking. The only way for you to end up back at home is for you to have stopped and turned around and come back home, right? Segments between A and B has no turning points. Yeah, I don't know what. Yeah, I don't know what the conversation here right now is going, but that's the idea, right? That's the intuition, is that in order to start at A and come back, you still had to return, right? Yeah, derivative is still zero if it's constant. Exactly. So here, let me leave this for now. What I want you to do is see if you can prove it. And Adam kind of had an interesting idea, right? Which is the gist of the proof seems to be to use the extreme value theorem and then to use the theorem that we just had. So why don't now we take our break, but on a scrap, like if you're taking notes and you don't want to ruin your notes, grab a scrap piece of paper and see if you can sketch out how this proof should go before I can even do it. And if you get it, that's phenomenal. That's really, really great, because this is a really useful, really important theorem. Even though we're just going to use it to prove a stronger theorem, this theorem by itself is actually pretty useful and pretty important. Okay. So let's take a 10-minute break. I have 10:02 or so by my watch. We'll come back at in 10 minutes at 10:12. And like I said, try and give this one a proof and see if you can manage to get it done, right? It's not too bad. Okay, so I'll see you in 10 minutes. Get started again. Hopefully you had a chance to look at Rolle's theorem and make take a stab at it. There are some like tricky cases that we have to be careful about just to make sure that we overcome. But let's see what we can do. And yeah, I had some chats with some students in via direct message, because I think most of you didn't see them. But yeah, I think generally kind of everybody has the idea, which is use the extreme value theorem, find a max or a min. That max or min, if it lies on the interior of the interval, because you know that your function is differentiable there, we can use the previous proposition to claim that the derivative is zero, and we're done. The only kind of pathological case that could happen is what happened if the max and min are at the endpoints, right? Like what if the max is at A and the min is at B? So we'll just take care of that case right away and we get rid of it. All right, so we say note that if f is constant, then f prime of x is just everywhere zero, right? It's identically the zero function, and so we're done. For all x in AB, so we're done. Okay, so now we're going to say, and you're like, okay, wait, does that really take care of that fringe case? It does, but we haven't set it up yet. So we're going to come back to it. So what we're going to do now is say, by the extreme value theorem, right? F achieves both its max and min. Its max and min on the interval AB. Okay, so what we want to do is we want to choose one of them. Oh, actually, you know what, too? I do want to say something here. Let me just move this down a little bit. Sorry, I even said that we were going to do this and then I forgot to do it. Okay, this is just a little note. You can probably put this anywhere. I would prefer to put it at the beginning, but if you just want to put it anywhere, that's totally fine. Without loss of generality, f of A equals f of B equals 0. Okay, if they're not equal to 0, define f hat of x, which is f of x minus f of A, and then and then apply the result. right? So basically what I'm saying here is you can basically take this function f hat, which is equal to f of x minus f of a. And remember, f of a and f of b are both equal. So f hat is also continuous on the closed interval, right? Because it's just f of x minus a constant. It's also differentiable on the open interval for the same reason. And if you show the derivative of f hat is equal to 0, well, the derivative of f hat is the same as the derivative of f, right? So just by vertically translating our original function, we're allowed to assume that f of a and f of b are 0, right? Because we can just define this new function f hat if it's not, and then the proof is just the same thing, right? So we're going to assume that they're both 0 just to make our lives a little bit easier. Okay, and then we can continue. So if the function is constant, its derivative is identically 0. By the extreme value theorem, f achieves its maximum on AB. Now, the reason that I wanted to be able to assume that f and a and f of a and f of b are both 0 is for the following sentence. So by the extreme value theorem, f achieves both its max and min if the max and min, or what do I want to say here? So if f is not constant, one of these must not be 0. Right? Do you all agree? Because if both the max and min are 0, the function is 0, right? So if the min and max are 0, that means that 0 is less than or equal to f of x is less than or equal to 0 for all x, which implies that f of x is a constant function, and that contradicts the fact that we're saying here, if f is not constant, one of these numbers is not 0. Does everyone agree? That makes sense, right? Okay, so one of the max or min is not 0, and here's the useful part. Yeah, you don't know. It's possible that both of them could not be 0, but the point is that they both can't be 0. They can't both be 0. Right? Does that make sense? Okay, good. All right. So let's assume that it's a max. And once again, right? So assume the maximum is not 0. And again, otherwise, apply the result to negative f. Okay, so the fact that the maximum is not 0 means it cannot be one of the endpoints. So let's say let C be a point in AB so that f of C is the global max. Note that C is not equal to A or B, right? Because f of A and f of B are both 0, but the function is not 0, but f of C is not 0, so C can't be either A or B. Does that make sense as well? Everyone agrees it's not one of the endpoints? And because it's not one of the endpoints, it must be an interior point. Thus C is in the interior. And by our proposition, f prime of C is equal to 0. And we're done. Okay, so unfortunately, it's a sort of thing that requires a little bit of writing. But again, the core idea of the proof is just apply the extreme value theorem pick out one of the max or min, argue that the derivative is equal to 0 there. Oh, what's the only bad case that could happen? Oh, the max and min are both at the endpoints. Well, in that case, your function was a constant and you satisfied the result anyway, right? Okay, any questions? Why is there a dot undefined? That's a weird. There we go. That's good. Everyone's okay with that? Okay, I'm going to assume yes, because I'm not hearing any protests. All right, let's do an exercise of this. It's a proofy exercise, though, not a computational one. So let's say that I tell you that I'm going to give you a function and its second derivative is never 0. What I want you to do is to prove that that function has at most 2 roots, right? So suppose f, let's just say r to r, is differentiable and f double prime of x is not equal to 0 for all x. And r, show that f has at most 2 roots, right? There's at most 2 points where the function f itself is equal to 0. Okay, I'm going to give you, this proof actually really isn't very long, but I'm going to say, let's say 4 minutes. Okay, so I'll give you 4 minutes to see if you can make any progress on this. And you're going to want to use, Rolle's theorem right up here like that. Okay, 4 minutes, see if you can do it. Okay, so let's give this a shot. Let's see if we can do it. I kind of had some interesting chat in the chat, which was namely like, oh, does this condition that f double prime of x is not zero guarantee that it's either strictly positive or negative? And for most functions that you can think of, the answer to that question is yes. However, the answer in general is no, right? There are twice differentiable functions such that f double prime is not continuous. And if f double prime is not continuous, you can't guarantee that it's sign definite, right? It's entirely possible that it's negative at one point and then jumps to become positive. So we can't actually even make that assumption. But luckily, we don't actually need it in order to be able to do this. Now, hopefully you look at this and you say, oh, this is begging for contradiction, right? Because you want to show if it has at most two roots. It's possible that it has no roots. It's possible, that it has one root. It's possible that it has two roots. So I don't want to try and think of those three cases at once, or I don't want to try and do those three cases separately. It's kind of best to go by contradiction and assume that it has more than two roots, right? Because then I can actually do something. So for the sake of contradiction, suppose f has three roots. Okay, now you might protest and you might say, well, no, contradiction would assume that it has more than two roots. So it could be three or four or five or however many. That's true. But if it has five roots, then it definitely still has three roots, right? So we're going to say, assume that it has three roots, because even if it has more than that, that's fine. Just choose three of them. We don't care which three you choose. Okay, so suppose that it has three roots. Let's call them R1, R2, and R3. Okay, and I'm going to put them in order, which you can definitely just always do. You're given three numbers. You can just say put them in order. And now what I'm going to do is I'm just going to apply Rolle's theorem a whole bunch of times, right? So note that f is continuous on R1, R2, and R2, R3, right? Because it's differentiable on all of R. And since it's differentiable on all of R, it's also certainly continuous on all of R. And so therefore is continuous on any, subinterval. And differentiable on the open intervals, once again, because it's differentiable on all of R. So it's definitely differentiable on any subset. And finally, f of R1 equals f of R2 equals f of R3, right? Because they're all equal to zero because they're roots by definition. So by Rolle's theorem, that means there exists, let's call it C1 in R1, R2, and C2 in R2, R3, such that f prime C1 is equal to f prime C2 is equal to 0, right? Now, certainly C1 is less than C2, right? Because C1 is less than R2 and C2 is bigger than R2. So C1 is certainly less than C2. F prime is continuous on C1, C2, right? Because it's differentiable. So since f is twice differentiable, that means that f prime is differentiable. So since f prime is differentiable, it's continuous. So f prime is continuous on C1, C2, and differentiable on the open interval. So by Rolle's theorem, again, there exists some number D1 in C1, C2, such that f double prime d1 is equal to 0. And that's a contradiction because we said f double prime is never 0. Right? So what did we assume in order to arrive at that contradiction? We assumed that we could find 3 roots. Therefore, we can't find 3 roots, so there's at most 2 roots. So thus f has at most 2 roots. Right, and we're done. So any questions about that? And you can imagine, right? If you're typing up a question, please continue. You can imagine that you can just continue to bootstrap this, right? And then basically you can say if f is n times differentiable and the nth derivative of f is never 0, then f has at most n roots, right? And if you want to prove that you can, you should probably do it with induction, basically done the base case here. So now inductively try and state and prove that more general result, right? So I have a direct message that says, when we say 3 roots, is it implied that they are 3 different roots? Yes. Yeah. Necessarily, they are different roots. We are not, counting roots with higher multiplicity as being multiple roots. Yeah. Fundamental theorem of algebra. Let's see. I mean, you certainly can prove the fundamental theorem of algebra from the mean value theorem, or at least the real valued version of the fundamental theorem of algebra. Does anyone know the real version of the FTA? Well, it would definitely be, so you can definitely say that a degree n polynomial has at most n roots. So you could definitely do something like that. And so in some sense, yes, you could prove that theorem from this. So yeah, this is, like I said, this is what I would do. So you can imagine the generalization of this is that if f is n times differentiable and its nth derivative is never 0, it has at most n roots. But the fundamental theorem of algebra, the real version of the FTA, is slightly stronger than that. Okay, it doesn't just say that a degree n polynomial has at most n roots. The fundamental theorem of algebra for R says that any polynomial of degree greater than 2 has a root, right? So because certainly you can say it's not too hard to prove that a degree n polynomial has at most degree n roots. The more interesting thing is any polynomial of degree greater than 2 has a root, guaranteed has a root, right? And that's the idea. Can I explain with a simple graph? It's a little bit hard. I can try. Kind of the problem here, though, is that you have to look at the graph of the derivative, right? But let's see what I can do. So let's see. So let's say I have 3 roots, right? And also it's a little bit hard because we're living in contradiction land, right? Because there definitely is this thing that I've just drawn definitely has a point where the second derivative is equal to 0. But let me do my best to try and show you what will happen. So here's R1 here, right? Here's R2, and here's R3. So by Rolle's theorem, there are points that make the derivative equal to 0, right? Or maybe I should draw maybe C1 here like this, C1 like that, and C2 like this. Okay. And now the idea is that because the derivative is equal to 0 between C1 and C2, there must be a point between C1 and C2 where the derivative of the derivative is equal to 0, right? And that point, say, is like, let's maybe say this point here or something, right, is D1. And I've kind of drawn it, unfortunately, so that R2 is pretty close to where the derivative flips, but let's see. Let's say I said this is the point, right? So basically between any 2 zeros, you know that the derivative has to be 0 itself, right? So between any 2 roots of the original function, the derivative must also have a root. Does that make sense? That's basically what Rolle's theorem is saying, right? Now, Rolle's theorem doesn't necessarily say it has to be a root of f, just 2 points where f is the f of a and f of b are equal. But if we let a and b be roots, Rolle's theorem says between any 2 roots of f, there's a root of f prime, right? There's a root of the derivative. So what this theorem is saying is, look, your second derivative has no roots. So if your second derivative has no roots, that actually restricts the number of roots that your original function could have had, because between the blue roots, between each of the blue roots, there must be a green root. And then if you have more than one green root, then there must be a red root as well. And that's a contradiction, because we said the red root would be a root of f double prime, and f double prime doesn't have any of them, right? So that's the picture, right? Between any two roots of f, f prime has to have a root. So the green are roots of f prime. So therefore the f double prime must have a root between them, and that's not allowed. Does that clear it up a bit? Is that better? And yeah, Stephen, your proof is exactly right. Of course, you have to be like, strictly speaking, when you write it out, you have to make sure you've satisfied all the hypotheses for Rolle's theorem and all that. But yeah, exactly. Your proof is the gist of the idea. Yeah, right. It's just between every two roots of f, you have another root of f prime. Okay. If f has n roots, will f prime always have n minus 1 roots? Yeah, and effectively, and f is differentiable and all that stuff, right? As long as you have the conditions of Rolle's theorem, then yes, you are guaranteed that, right? Because again, and again, distinct roots, right? So if f has n distinct roots, then you can guarantee that f prime will have n minus 1 distinct roots. Yeah. And so you can see that there's this, again, this nice sort of induction thing you can do. So you could prove that by induction, and then you can then bootstrap, well, if f prime has n minus 1 roots, then f double prime has n minus 2 roots, right? And if f double prime has n minus 2 roots, then f triple prime has n minus 3 roots, and so on and so forth. So you can kind of like push it up the derivative chain like that. All right, so here now is the master theorem. And this is easily one of the great theorems. This is the mean value theorem. Okay, so the statement of the mean value theorem starts off almost identically to Rolle's theorem, but it's slightly more general. So if f maps AB to R, exactly the same so far, is continuous on AB, same thing, same as Rolle's theorem. And differentiable on the open interval. And now here's where it changes. There exists a point in the open interval AB such that f of b minus f of a, how do I want to state this one? Let me write it like this. I don't like writing it like this, but I'm going to do it just to maybe give you a little bit more insight. The way I typically write this is not as a fraction. So let me just put it in brackets though. Like so. Okay. So those are the same, obviously, right? B and A are not equal. We're going to say that B and A can't be equal here, just because otherwise the function is not differentiable, so the theorem is meaningless. So A and B aren't equal, which means you can divide by it. So the left-hand side and the right-hand side are exactly the same statement, where I've just multiplied both sides by B minus A. Okay. So again, you can see that the start is the same. And in fact, this theorem implies Rolle's theorem, right? Rolle's theorem is a special case of this theorem, because if f of A equals f of B, then if you look at this thing on the left-hand side here, let me say comment, the MVT implies Rolle's theorem, since if f of A equals f of B, then what do we have? We have f prime of C is f of B minus f of A divided by B minus A is equal to 0, right? So Rolle's theorem falls out from the mean value theorem. It's a special case of the mean value theorem. So there's a very real sense in which from now on, we will never refer to Rolle's theorem ever again. It will always just be a special case of the mean value theorem. That being said, we're going to use Rolle's theorem to prove the mean value theorem, which means that Rolle's theorem implies the mean value theorem. So these two theorems are actually equivalent. They are the same theorem, just written in slightly different ways. Okay. Now, I'm going to show you geometrically what's happening, because the geometric intuition behind the mean value theorem is nice and it helps with the proof, even though the geometric intuition is useless in practice. Let me see here. I want to draw this picture big, so I'm going to kind of scroll down, but I'll zoom out when I'm done so you can see the theorem and the picture. Okay, so here's A. Here's B. And then what I'm going to do is maybe let me try and use the pencil here. So I've got this point here. I've got this point here. I'm going to try and draw the secant line. Hey, that's not too bad. Okay, so I've got this secant line and the slope of this line. No, let's not use the pencil for that. So the slope is f of b minus f of a divided by b minus a. And then what the theorem says is that there's some other point on the graph between A and B whose tangent line has the same slope. Okay, and just kind of eyeballing it, to me, it looks like this. It looks like it's that point. Right? So there is a point in AB whose tangent has the same slope as the secant between A and B. Okay, so let me kind of zoom everything out here. So Rolle's theorem is a special case of the mean value theorem. Yes, yeah, exactly. And it's not even necessarily when the left-hand side is equal to 0. It's just that when Rolle's theorem happens, you know that f of a is equal to f of b, right? Like that's the difference in the hypotheses between the mean value theorem and Rolle's theorem. Rolle's theorem says f of a is equal to f of b. But if you take that and you plug that into the result of the mean value theorem, then you get that f prime of c is equal to 0, and that is the result of Rolle's theorem, right? So if you take the extra hypothesis of Rolle's theorem, plug it into the MVT, you get Rolle's theorem out. Okay, so does everyone see that this is geometrically what the mean value theorem is saying, right? That if you take the secant line between A and B, that's this f of b minus f of a over b minus a thing. That's the slope of the secant line. There's some point inside of the interval AB whose tangent line is the same, right? Because that's what f prime is, right? It's the slope of the tangent line. So it's saying there's some point inside whose tangent slope is the same as the secant slope. Now, this is really important for the proof. Okay, this geometric picture, super important for the proof, completely useless for any application whatsoever. Why would you ever possibly care whether there's a point inside whose tangent line has the same slope, right? The answer is you don't. So I'm going to talk about the applications in a second, but let's just focus on the proof for now. And the way that the proof is going to go is as follows. So in the proof, what we're going to do is we're going to try and reduce this to Rolle's theorem. So what we want to do is basically take the graph, which you can see right now is kind of at a slope, right? And what I want to do is make it so that both the secant and the tangent lines become horizontal. Okay, that's the idea. So basically, I want to just transform this function basically by rotating it about, the point A. I want to rotate it so that both of these lines become horizontal. And the way that I'm going to do that is I'm going to look at the difference between the function itself and this, hold on, let me just double check here. Yeah, actually, sorry, between this secant, right? So I'm going to take the function and I'm going to translate it down exactly by the difference between the secant line through A and B and the function of the graph. Okay, so I'm going to do this translation. After I've done this translation, my graph, sorry, I'm going to end up kind of drawing over to the right here, will look something like, what will this look like? It'll look something like, and then my secant line will now be horizontal, like so. And then I'm looking for that point. Okay, unfortunately, I've kind of drawn the yellow line. Maybe let me put the yellow line a little bit further down so it doesn't get in the way. Does that make sense? And this is just exactly Rolle's theorem now, right? Because whatever this new function is, you'll have that f of a and f of b are equal. And so you're just looking for a place where the horizontal lines are the same. Won't the translation be the other way around with the arrows? Depends what you here. I'll write down the function and you can see it firsthand. Let me just double check here. I'm going to take the function and subtract the secant line. Should A and B be on 0? No, they just have to be equal, right? For me to apply the mean value theorem, they just need to be equal. Or sorry, for me to apply Rolle's theorem, they just have to be equal. Here, let me write down the function. Right? Okay, so the proof is very quick. So I'm going to say define a function capital F, which is little f minus the secant line. Okay. So, I mean, my picture is not entirely representative. What I'm actually doing is subtracting. I guess actually what I should do is say that I'm actually subtracting, let's see, x minus a. So I'm really subtracting this slope here, right? Where I basically took that secant line and dropped it down so that it passed through A. That's actually what I'm doing. But I think that that picture is a little bit harder to draw because the picture is just going to start to get really, 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 really crowded now if we really want to do it. Right? So now what I'm really doing is this. Right? But you can see that this picture, I think, is a little bit. Okay, so that's actually what's happening. Okay? Right, does everyone agree that that's what this function is doing? And hopefully you see this is going to make the lines tangent or the secant line horizontal, right? By precisely kind of what I've done is I've pulled everything down. Let's just check, right? Let's check. So note capital F is continuous on AB, right? Because what are, look at like that secant thing, f of b minus f of a divided by b minus a, that's just a constant, right? This thing here, this is just a constant. It's some number. So where are the functions? This is a function. And this is a function right here, right? And you know f is continuous. You know that x minus a is continuous. So this is just a sum of continuous things, right? And it's also differentiable on the open interval for the same reason. And differentiable on AB, right? So by doing this, shifting down, we haven't done anything crazy, like we haven't broken continuity or differentiability. So it's continuous on AB, differentiable on the open interval AB. And then moreover, if we compute what f of a is, That's certainly just f of a, right? Because if you plug a into this, that whole secant line stuff just becomes 0, right? Because if I plug a into the x minus a part, that part becomes 0. And then if I plug f of b into this, okay, so we have to think about this one a little bit. So what am I going to get? I'm going to get f of b minus all this grossness. The b minus a's, I'll get a b minus a in the numerator and the denominator. They'll cancel. So I'll get f of b minus f of b minus f of a. Exactly. So we get f of a as well. Cool, right? That works, right? Because it actually just pulled the other end down. So this pulls everything down now. So what do we have? So by Rolle's theorem, there exists some point C in AB such that f prime of C is equal to 0. But if you compute f prime of C, it's actually really easy. You know, capital F looks a little bit gross, but it's actually really easy to differentiate. Right? It's the derivative of little f. And then again, that term on the right is just some constant times x minus a. And we know how to differentiate that. You're just going to get the constant out. Right? And so we're done. Right? Because if you, like, I hope I don't have to rewrite it out, but you can see if f prime of c minus the secant line is equal to 0, that's the result that we wanted, right? So the proof is actually really quick, right? Because with Rolle's theorem, it's just straightforward. Okay, are there any questions about that? When we plus in f of a to f, don't we get 0 in the denominator? Plug in. When we plug in f of a to f, just a, you mean? No, because it's just b minus a in the denominator, right? There's no x's in there. Yeah, so where we get, the only place there's an x is right here, right? So when we plug a into here, we'll get a minus a, which is why that whole thing dies. But, right, just keep in mind, this thing here is already a b, right? Like it doesn't have any x's in it. How you construct f of x? So it is this picture. It's exactly this picture right here, right? With the idea that I've got this thing that might be on a slope. My goal is to turn it into this thing because I want the secant line to be horizontal. And by virtue of that secant line being horizontal, right? So this blue thing that I've drawn here, this is y equals capital F. And now capital F, sorry, this is just A. And this point here is B. And so if I've drawn this correctly, I've tried to draw it so that the height of the left endpoint is the same, right? So that basically this, right? The left endpoint doesn't change, but basically you've now rotated. It's not a perfect rotation. There's some shear involved, but effectively you've kind of rotated the graph now so that that secant line is now horizontal. By virtue of that secant line being horizontal, it guarantees to you that capital F of A is equal to capital F of B. And now all we do is apply Rolle's theorem, and then effectively we just rotate it back up, right? Like that's where the idea for f of x comes from. Right? So it's the construction of big F is the blue thing on the left, the blue graph. Then you take the black dashed line, that's the equation of the secant, but not exactly the equation of the secant, just you want it to go through x minus a. And then you just translate down by that amount. I guess, okay, no, my picture again is bad. I guess really I should draw these arrows. So here's the problem. This picture is a little bit hard to draw, right? Because really the amount that I'm translating down is this amount. But how do I draw this amount? Oh, no, I guess, yeah, no, my original picture is fine, right? This is what I'm translating down. Right? Because what I'm doing is I'm taking this amount. So if you took the black dashed line, that's the weird, this thing right here is the black dashed line. Okay. And if you subtract that amount, so here might be this amount. And so what you're going to do is you're going to take the blue line and subtract that down. And so what does that actually look like? Well, that looks like this arrow, modulo, my drawing ability. You would take that, you would draw that down, and that's basically how you figured it out, right? You just subtract that down. Okay, so this is a little bit hard to draw, but basically you magic it so that it works out. Yeah, that helps as well. Which is f of x. The blue thing is little f. Yeah, so I guess the better picture is to do something like, that's kind of the better picture. But I don't think it's as nice to kind of see what's going on, right? So technically speaking, the picture that I had drawn before, they weren't as pretty, but the idea was just to give you the motivation behind what's going on. But this is really what's happening, right? Is you're taking the length of the secant line and you're dropping everything by that length. What is the gray line? That is the secant line between A and B, right? So it's the thing whose slope is this. Yeah, you could think about it kind of like changing a coordinate system. I don't think that that's a terrible way of thinking about it. Like basically you're almost just saying, I'm going to turn my head to the side so that the lines look horizontal now. You can kind of think about it like that. I don't think that's a terrible way. That being said, there's a formal mathematical definition of changing coordinate system. I do not think that this satisfies it, but you can think of it as like changing your reference frame, right? And just kind of saying like, I'm going to turn my head to the side and look at it like that. Okay. Is this all right? So we're out of time, so I'm not going to be able to tell you why this is useful. Again, this geometric picture here is useless, okay? This is not how the mean value theorem is ever used. The geometric picture here is just to kind of give you an idea of how the proof works and maybe a nice geometric idea of what the mean value theorem is saying. But in practice, the mean value theorem is never a geometric thing. The power of the mean value theorem is precisely in this equation right here. Okay, and I'll elaborate on this a little bit on Thursday, and I'll tell you like why this theorem is like why this result is useful. But basically, in a nutshell, it gives you the ability to translate between the infinitesimal stuff with the derivative and the non-infinitesimal stuff in the function itself, right? It's like a Rosetta Stone. It gives you the ability to write things about f in terms of f prime and vice versa. I'll go into that in a little bit more detail, but we're already over time today, so I don't want to get into it in too much right now, but that's the idea. And then we'll do a whole bunch of examples and I'll show you exactly how useful this theorem is. Okay, everyone? So that's going to take care of us today. Yeah, hopefully there's kind of a lot to unwind here. So spend some time and look at it. Yeah, I think this is definitely one of my favorite theorems in like first year analysis. It comes up a lot in second year too. It's really, really important. But there's definitely a lot of stuff here to process. So, take your time. And if if you're feeling a little bit overwhelmed, I think that's okay. There's a lot here, but spend some time, think about it a little bit, and see if you can make heads or tails of it. And we'll talk about it a little bit more on Thursday. And we'll see it in action on Thursday. Okay? So thanks, everyone. Thanks for dropping by, and I will see you Thursday morning.